Hi everyone, take a look at equilibrium 2. So kind of an extension of what we already learned. So nice little review here, okay. So remember, a chemical equilibrium, we like to, in the book at least, use a generic equation, right? So here we have A moles of reactant A react with B moles of B. And you know, this is the best that Word can do when I wrote this. It's actually like that dynamic equilibrium sign. Now remember, dynamic equilibrium means there's exchange between reactants and products. Their relative amounts stay fixed. So their ratio is fixed, but there is exchange between them. Remember we talked about the revolving door? As one reactant turns into product, one product turns into reactant. Same number both sides, but there's exchange, right? Revolving door. Okay, so A of A, B of B, C of C, and D of D. Now remember, it's always for our equilibrium constant, and equilibrium constant is a measure of the relative amounts of reactant and product, right? And it's defined as essentially products over reactants, all right? And it's a fixed ratio. So K, and some folks have brought this up from their lab, yeah, K is always the same number. It doesn't matter how much reactants you start with. You can change the numbers of the reactants, yeah, but they'll always settle to be a fixed ratio of reactants to products. So when you did that lab, you should have got a similar value for K for each trial, even though you started with different amounts of, you know, iron and thiocyanate. Okay, and you know, quantitatively, products over reactants, and we'll see this as we go through. It's basically the next kind of math function up, right? So we added reactants, it's products over reactants. So reactants are underneath, they were added here, so they're multiplied here. Their concentration is multiplied. We up here, if you like, there's A of A, so let me 2H2O or something, right? So the stoichiometric constant, there's two of them. We actually raise it to the power. So a multiplier is raised to the power, the stoichiometric constant to the power, added reactants, multiplied reactants. Okay, so if you're going to remember one kind of neat little math trick for equilibrium, for K it's always the next thing up, and we'll see this as we go through, right? So when we add equations, we'll multiply K's, things like that. Okay, so it's always the next kind of function up on the on the food chain of math, right? Food chain of math, trademark. All right. Now, if you remember, because this is basically, you know, just paraphrasing, products over reactants, right? And it's a fixed ratio. So in a beaker at the end of a reaction, there's some reactant left and there's not all product formed, right? So there's an amount of both, yeah? That ratio, products to reactants, is K essentially, right? With the math thrown in, all right? Now, if you think about it, if there's lots of products, that means we're on the right side over here, right? So if there's lots of products divided by reactants, K will be a large value. So we like to kind of link these two together. So if K is large, equilibrium lies to the right. Lots of products, it's a top-heavy fraction, right? If K is small, and when we say small, we mean less than 1, because equal numbers cancel out to 1, right? Or divide to make 1. So if K is small, less than 1, we say it lies to the left, okay? So small K, lots of reactants left at equilibrium. Large K, more products at equilibrium, but both still in there in measurable amounts, okay? All right. Now, I'm actually going to show you this slide here. I'll show you this one first, right? So this is actually a nice slide. It may look familiar, right? It should look familiar because it's a graph of concentration versus time, right? So I'm actually going to do double origami, right? So if I did that, now that looks super familiar, doesn't it, right? So this is the decay away of reactants and the formation of products, right? Now, do you think that K for that, so if you think about it, right, eventually that line, the red one and the blue one, the amount of products and reactants will go flat, meaning we're, you know, before we said we're not making any more, but we're making equal amounts at the same rate, right? So there's an exchange here. So when we get past that point, products and reactants are exchanging like in that revolving door, but because, you know, for every one I make, I lose one kind of thing, it's a revolving door, equal amounts, right? So that's why the line is flat, yeah? So once the kinetics is over, and that should look very familiar from kinetics, we get that flat line, the rate of formation and rate of loss is now flat, right? The slope is 0, right, essentially for a flat line. So there's no rate of change, it's not moving anymore, right? It's finished, right? So it's complete reaction past that line. And there's our ratio of products to reactants. And K here has to be, if you think about it, large because there's more products than reactants. And that's what we want in a chemical process, if it makes sense, right? Because we always want to make more stuff than what we leave behind. We want to make things, right? So that's your normal plot, and we saw that in the kinetics work, okay? But what happens if K is small? Without peaking, what do you think happens, right? Well, if K is small, there's going to be less products and more reactants at equilibrium. In other words, we're not going to get this point here. They're not going to cross, right? So if you want to think about it in very simple terms, at that point, K is probably close to 1, isn't it? Because there's equal amounts there, right? So if it ends up more products than reactants, K's big. If we see over here, it never got there, did it? It never got there. So here, look, less products, more reactants. Products on top, small number. Reactants on bottom, big number. It's a fraction, right? So it's smaller than one number. K is small, lies to the left. All right. So there we go. We can do that, right? So there's more reactants, lies to the left. So associate lying to the left with more reactants at equilibrium, lying to the right with more products at equilibrium. If you want to work out the numbers, we use this. This is a qualitative kind of assessment. Products over reactants. Large number of products. That fraction is going to be bigger than 1. Larger number of reactants, that fraction is going to be less than 1. Makes sense. Okay, so hopefully that's good. That's kind of a review from last time. So we record K at typically a specific temperature. Okay, the value of K will change with temperature, so we like to do it at a fixed temperature. All right, usually standard conditions, 25 degrees C. But we will often quote the temperature just to say, hey, we did this at whatever the temperature was, so people can, repeat it later if they need to, right? Because we always like to repeat other people's work. Okay, so since the value of K is fixed, okay, at a specific temperature, okay, so is that ratio products to reactants. So products, concentration, or pressures if they're a gas, is a fixed ratio, which, obviously we call K with the math involved with the stoichiometry. Yeah, there's more details, but hey, products over reactants is essentially K, right? And it's a fixed number at a specific temperature, okay? So if there's a fixed ratio of products to reactants, yeah, if you think about it, it doesn't matter where we start. If we throw a bunch of reactants in a test tube, they'll react to form products, right? Maybe they stop halfway, so there's equal numbers of reactants and products. Fair enough, K will be 1, right? But what if I'm to throw a bunch of products in there? They go in the reverse reaction to make reactants and end at ratio 1 to 1 maybe, okay? So here it is here. It's a bit like a glass half empty, glass half full situation. Because we always end up with measurable amounts of reactants and products at equilibrium, right? That ratio is a fixed number, right? That means it doesn't matter what direction we approach that equilibrium. We can start with all reactants and make some products. We can make with all products and make reactions. Glass half empty, glass half full. It's one of these deals, right? Okay, and we eventually end up here. Hopefully that makes sense. All right, so we can, reaction direction is really just a definition, right? We write down typically left to right, don't we? Right? We like to think about reactions going from left to right. Okay, so for the forward reaction, equilibrium is products over reactants, right? That is just what we've learned so far, yeah? However, if I go in the reverse reaction, it would be going the other way. It's like I threw all the products in and it went to equilibrium, right? So if I go from B to A, products would be A, reactants would be B, so it would be switched, right? So for the reverse reaction, I'm going from what we defined earlier as products to reactants. So hey, products over reactants would be A over B, switched, right? Hopefully that makes sense, okay? Now what about derivation? What about derivation? Now be careful, right? Because K forward equals products B over A. And we know K rev equals kind of just this switched, right? Well, what's a simple function that does that? It's 1 over, isn't it? So 1 over K forward equals 1 over B over A. And it's a nice trick. 1 over the something equals, it's been inverted twice, right? A over B. Ah, there it is, right? So K rev equals 1 over K forward. Okay, so there it is. So that's your kind of take-home message for the math, right? If you have a numerical value of K, say it's 2, right? K forward is 2, K reverse is 1 over 2.5, right? So you can easily just take the reciprocal to get K for the reverse reaction. Okay. Here's a classic. As I'm sitting here working through this with you, I have this story in my head I'm going to tell you, and I'm going to look online for some pictures, hopefully video, to kind of show you this kind of scary thing, right? So here's HF, right? And if you remember your periodic table, hydrogen, chlorine, bromine, iodine. So if I make HCl, that's stomach acid, right? HBr, hydrobromic acid, also a super strong acid. HI, again, group chemistry, super strong acid, right? So we're familiar with HCl, all right, super strong acid. When I look here, HF, when it dissociates to make, H plus is what's responsible for acidic behavior, K is super, super small. So let's answer this question first, right? Do you think HF is a strong acid, yes or no? Well, K for that direction is a small number, less than 1, 0.00064, right? In kind of 1, 2, 3, 6, 4. So it's a super small number, right? So that means the ratio of products over reactants is a small number. So that means there's much less products than reactants. So if I was going to draw that, I'd not draw that sign, I'd draw this sign, right? Yeah. So it lies to the left. Nope, left. Okay. So when we have a number less than 1 for K, as we saw on the first page, products over reactants is a number less than 1. That ratio is less than 1, so it must be bottom heavy, if that makes sense. Okay, so there's more reactants at equilibrium than products. All right, so I'm going to say it's very weak. And that is true because K forward is small. All right, so think about the ratio when you think about that. Okay, now the story. Okay, when you buy something like Grey Goose vodka, that's the only one I can think of, right? It's etched glass bottle, isn't it, right? So the bottle is very nice and fancy because it's got like a Grey Goose on it, which is like etched in there, right? And how do they etch glass? Well, they make a mask, right? So they put this kind of piece of plastic over it with like holes in, okay? And then they put that in the vat of acid, and the acid eats away the glass, and then it becomes frosted where it's been eaten away a little bit. Interesting, right? It turns out if you put glass into HCl, I mean, you've probably seen this in lab, when you put HCl into a test tube doesn't dissolve, right? So HCl doesn't dissolve glass. However, because of some unique chemistry, HF will. Okay, even though it's a weak acid, you don't get much bang for the buck in terms of acidic behavior, but it will dissolve glass, right? Okay, and I actually do that balanced equation back in Chemistry 101 if you want to check out those equations later. Okay, it's just real quick. Silicon dioxide plus HF turns into SiF4 plus H2O, right? So you can balance that at your leisure, right? Okay. Now, bottom line is it's a weak acid, yeah. So, if you spill a strong acid on you, it burns, right? If you spill a weak acid on you, you tend not to notice, right? If you spilt vinegar and didn't notice, you wouldn't, unless you touch yourself, oh, it's wet, right? You don't notice any kind of stinging when you spill vinegar, or even pop, right? Soda has carbonic acid, which is just as strong as vinegar in terms of acidity, all right? So you don't really feel a weak one because it doesn't burn, okay? HF is the same, it's a weak acid, it doesn't burn. HF is actually a weaker acid than soda. Interesting, okay. Now, so you work in the Grey Goose bottle factory and you're etching your bottles with hydrofluoric acid, HF, right? And if you spill it on yourself, it's a nightmare because you won't notice because it's weak. And what it actually does, it has an interesting chemistry, right? So it absorbs into your skin, it actually absorbs through the skin. And bone is a lot like glass, right? It's calcium phosphate, silicon dioxide, it has similar somewhat chemistry, right? And you'll actually dissolve your bones from the inside, okay? So it's one of the worst ever industrial accidents you can see, right? So if I can find a picture, I'll show you, how they make this this etched glass, but the people are wearing like, head to toe, 1.5-inch thick rubber suits, showers everywhere, it's super, super, super careful when they do that. Okay, so that's my story. Now, what's K rev? Well, remember, K rev equals 1 over K forward. So just stick the numbers in. Pause me, come back. All right. Stick the numbers in. 1 over this number, 6.4 times 10 to the minus 4 equals 1.5 times 10 to the minus, 10 to the plus 3, careful there. So that means for the reverse reaction, when we go from products to reactants, it's a large K, right? That means, hey, the equation's reversed now, so what was previously reactant is now product. K is super large for that process, so it's in favor of this undissociated, right? Okay, so for the reverse reaction, HF is a product, K reverse is very big, lots of HF, glass half empty, glass half full. If I just think about the forward reaction, K forward is very small, so again, less products, more reactants. It's telling you the same thing, just from a different point of view. Okay, now, more equilibrium math then. So, remember my little kind of golden rule, right? So it's always the next kind of function up, right? So when we kind of saw we were adding reactants or products, we multiplied them in the equilibrium expression. When we're having stoichiometric multipliers, we put them to powers, right? So K always seems to be that next power up in terms of what's going on in the test tube, right? Okay, so if I look at this one here, very simple. Whenever we have a multiplying power, right? So if I have 2HF, for example, that'll be squared in the equilibrium expression, okay? So let's look here, this is an example, right? So if I look here, I've got 1, 1, and 1. So in our regular example, I got one reactant, one product, one product. If I just multiply through by 2, and that's the trick, you're multiplying through everything by the same constant, right? So I'm making twice as much stuff, I'm multiplying by 2, right? Yeah. So I multiply through by 2. What's K? Well, if I multiply the reaction, I do that to the power for K, right? So K equals 6.4 times 10 to the minus 4. Because I've multiplied through by 2, I'm going to put it to the power of 2. Ah, okay, got it. So if an equilibrium expression is multiplied through by a constant value, multiply through by 2, the K value is raised to that power, in this case 2, which equals, let me get this right, 4.1 times 10 to the minus 7. Okay, fair enough. Now, you remember your math tricks, right? Multiplying by a half is really dividing by 2, isn't it? Right? So I can use the same trick here. So if I multiply 3 by 2 here, I multiply through by a half there, so it's going to be 6.4. Don't get confused by it. 10 to the minus 4 to the power half. Power half is square root, right? What's the square root of that? 2.5 times 10 to the minus 2. Fantastic. All right, hopefully that makes sense. Hopefully that makes sense. Now, here's the super fun part, right? So you can combine them, right? You can mix and match, right? So remember, if I go reverse it, if I reverse it, it's reciprocal, it's 1 over, right? If I multiply it by a constant, it's the power, right? So extra credit, 1 point. What is, give you a big clue here, this is a reverse reaction, and it's multiplied by 3, okay? Okay, so just write that in your notes, take a picture with your phone, email me that picture, all right? You wouldn't do that on a test, of course, right? But hey, just for extra credit, work out, okay, I'd like you to do like we did the math here, but for this process. Remember, it's a reverse reaction, and it's multiplied through by 3. Okay, all right. Okay, so we multiply through by a constant. For the reaction, we raise K to that same power, next function up, so to speak. Same thing here, if we add reactions, we actually multiply Ks. So if I have 2 reactions with different Ks, and I add them, that resulting reaction will have those Ks multiplied. So here's an example, right? So the equilibrium constant for a net reaction, so you add 2 or more reactions, okay, is the product multiplier of the Ks for those individuals, right? So simple expression I like to use is add reactions, multiply Ks, right? So why don't you try it, right? Remember how we did this before. Put everything on the left, everything on the right. So products, reactants, and then multiply these Ks. In case you're adding reactants, multiply Ks, right? Give it a shot. You're back, so let's do it. So 2HF plus 2H plus, that's oxalate, 2H plus, 2F minus, plus oxalic acid. All right, fair enough. Now, does anything cancel? That one, that one. What else? That's it, right? Okay, now, so the question says, what's K for this reaction? Well, it's the one I just got through cancelling. So it's going to be K1 times K2, which equals, now we do it down here, K3 equals K1, K2. Numbers, 4.6 times 10 to the minus 7, it's that one, times, 2.6 times 10 to the 5, which equals 0.12. Hopefully you got 0.12. Okay, now, very, very similar for this next one. Same, just practice, right? So try and work it through. The answer is 1.3 times 10 to the 5. If you don't get 1.3 times 10 to the 5, let me know, office hour or water cooler chat, right? Okay. Now, I've left myself a little note here, right? Do the NO example. So the NO example is here. Okay, now I introduced the ICE method in your equilibrium pre-lab. Okay, so I want to get it in your notes, all right? We will see this over and over again, particularly when we start looking at acid and base chemistry, okay? But I want to kind of show you that the ICE method is almost like a universal method. It's just that buffers and those kind of things, common ions, things like that we'll meet later, are just specific applications of it, all right? Now, when we do an ICE method for like regular chemical equations like this one, we have to use, tricks sometimes. Otherwise, as we'll see, we might have to use some kind of like quadratic equation or something. We don't want to use a quadratic equation. So we often pick ones where there's a shortcut. And this is no exception. All right. So let's take a look at it. So this is actually lab question 4, right? So on one of your labs in semester time. This is actually a post-lab question, right? So the air pollutant NO is produced from automobile engines from the reaction of N2 and O2. All right, fair enough. Both are 1.4 moles per liter, so that's my initial concentration. What's the concentration of each reactant at equilibrium? And they give you K. All right, so it's a bit like your lab, isn't it? Okay, you've done already. So ICE, first things first, write the equation, right? So the air pollutant, oh, there's the equation. It's already written. I'm going to rewrite it so it's nice and big, right? So N2 plus O2 is in equilibrium with 2NO. Fair enough, right? Then I could go ICE. Let's just decipher the question here, right? So initially, these are 1.4, right? Oh. Get sig figs. And initially that's 0 because we haven't done anything yet, right? So it's just like your lab, right? You kind of calculate the initial concentrations, throw them in a beaker and off they go. This is like throwing these two in a beaker and off they go, right? Before they actually kind of, right at the millisecond you throw them in there, they haven't done anything yet. Okay. Now change. Now here's where the stoichiometry comes in, right? If you remember, I mentioned in your pre-lab, sometimes it won't be nice, easy stoichiometry, 1, 1, 1. Here it's 1, 1, 2. Which actually works in our favor later, I'll show you. But watch this, right? So here, when I change, I'm going to go minus x. So one of these reacts with one of these to make 2 of these. I don't know how many I'm going to lose. We're going to call it x, but because 1 reacts with 1, we lose x of each, right? But wait a minute, 1 reacts with 1 to make 2. So here's the key thing. I'm making 2x there. Make sure you get that change line, right? So 1 reacts with 1. Don't know how many I'm going to lose, right? When I do my reaction, so I'll just call it x. 1, 1x, right? They make 2, so hey, 1, 1, 2, x, x, 2x, fair enough. The bottom line, the equilibrium, and this is where K is measured, right, at equilibrium, yeah? We got 1.40 minus x, 1.40 minus x, and then 0 plus 2x, 2x. Fantastic, right? All right, now, so therefore, K, which we have a value for, right? K equals products, NO, and it's 2 of them squared. reactants, one of each. Just multiply them out. Fair enough, right? Now let's keep our eyes on the prize, right? They want to know the values of these things here. Yeah, they want to know what is the concentration of each reactant at equilibrium. In other words, on the E line, right? This. All right. It's 1.4 minus x, 1.4 minus x, and 2x. So obviously we've got to find x. All right. So what we're going to do is the equilibrium math, right? So K is known. 0.0017 equals this guy squared at equilibrium. Careful, it's going to be 2x is the concentration, but you got to square it. You got to square it over this one times this one times this one. 1.4 minus x, 1.4 minus x. Now this is where, you know, unless it was a kind of a trick question, we'd have to do a quadratic, because when we kind of square everything out and multiply it out to find x, it's going to be 4x squared, isn't it, on top, right? And then whatever that would be as a quadratic underneath, x squared minus 1 point, yeah, you can do it, right? But we're not, right? So here's the trick, right? That equals 2x squared, yeah, got that already. Same thing times the same thing is the thing squared. This is the trick. Ah! Therefore, oh, sorry. Squared, squared, right? So therefore, if I think about it, if I take the square root of both sides, the square root of k equals 2x over 1.40 minus x. Okay, that's just the value. That's just 0.0017 square root, isn't it, right? You can solve for x. And if you work it through, what did I get? X equals, try it, right? 0.0283, right? Therefore, the equilibrium concentration of N2 is the same as the equilibrium concentration of O2, which equals 1.40 minus x, 0.0283, which is approximately equal to 1.372, whatever the units are, moles per liter, right? Okay. NO, 2x, 2 times 0.0283 equals whatever that is, 0.056. There we go. All right. So spend a little time on that. Okay. Make sure. Obviously I skipped. You know, if I look at my my notes from class, yeah, and you know, feel free to take a screenshot, right? So I didn't actually, you know, just trudge through the algebra here, right? So just, you know, just make sure that, you know, you solve this part. Square root of k is known, it's just a value, right? And you can just solve, you know, collect terms, and you can solve for x. Okay. So nearly at the end of my time, 27 seconds left. That's a good place to stop. I'll see you guys in a minute. All right, so equilibrium constant Kp. Now remember, we kind of talked about this a little bit. There's Kc, which is just often just generically referred to as K, and Kp, right? So Kp is when you measure concentrations actually as pressures, right? So remember, pressure and concentration are proportional. So you can actually use pressures in place of concentrations in equilibrium expressions, right? And you get a number, right? If you did the same math but with concentrations, the value for K would be slightly different sometimes, okay? So what this does, we're going to kind of relate the two. So you can easily actually convert between Kc and Kp, all right? But you've got to be careful, all right? There's an equation, all right? Now we had an interesting discussion today at the office hour, and it's all about the units, it turns out, okay? So we've got to be careful, okay? So let's take a look. So as we go through, this will make sense, all right? So for gas phase reactions, obviously it's easier to measure partial pressure, okay? So we get the Kp expression, we talked about that already. For solutions, regular K, or sometimes called Kc, All right, this is the equation that relates the two. So Kp equals Kc times RT delta N. And let's just talk about what those terms are. All right. Now, first things first. R, of course, is the molar gas constant. 0.08206 liters, atmospheres, mole, Kelvin, right? So if we measure our pressures in atmospheres, we're going to use 0.08206, right? All right, fair enough. Now this is what we noticed this morning when we had the office hour, the pressures were in torr. So you'd have to kind of divide them by 760 to get atmospheres, and that's where we had a little bit of an issue. Okay, so rule of thumb, atmospheres unless otherwise stated, okay? And if you do happen to use, if you like, metric units, 8.31 joules per mole per Kelvin. Remember that one from the Arrhenius work, okay? 8.31 joules per mole per Kelvin. Pressure has to be in newtons or pascals. Actually, newtons per meter is a pascal. So a pascal, right? So that's very, very rare. Probably never ever see that. So I guess the take-home message is whenever you work with Kp, right, use atmospheres as a unit. If only I could go back in time 4 hours, I'll tell the two students, you know who you are. That. Okay. Now, so let's talk through the equation. So you want Kp, so Kc is always given, you probably just look it up, right? R times the temperature you do the experiment at, times delta N. Now delta N is a change in the moles of gas. If you think about it, if I have 1 mole of gas turns into 2 moles of gas, I'm going to make a bigger volume, aren't I, right? So it's all about, you know, gases and partial pressures. So that's an issue, right? So we have to figure out the change in the number of moles of gas. So if you think about it, 1 mole makes 2 moles. What's the difference? The difference is 1, isn't it, right? So it's the number of moles I finish with, total number of moles of gas, minus the moles I start with, reactants, yeah? And in that case, it was 1 made 2. Delta N is just 1, right? Interesting. Now, special case. If it's the same number before and afterwards, delta N is 0, isn't it? Anything raised to the power of 0 is 1, right? So when delta N is 0, Kc equals Kp. All right, so that's a nice little trick. You only have a difference in Kc and Kp where there's a deficiency in the moles of gas before and afterwards. Do you make more gas? Do you make less gas? Delta N would be a number, not 0. Okay. All right, so here's some math for you, just to kind of remind you how this works, right? So remember, we did this before when we talked about osmotic pressure. PV equals nRT. Fair enough, right? The concentration of a gas, hey, moles per liter. Moles is N, liter is that, right? So N over V equals P over RT. That's where that comes from. Okay, so there's a relationship, okay? So RT just pops out from there. Okay, so if I just concentration equals P times 1 over RT. All right. So that's where it comes from. Oh, move it up, sorry. So there we go. So that, you know, that's not necessary math. I just wanted to show you where the RT term came from because, hey, PV equals nRT, moles per liter is concentration, N over V, which is P over RT. So that's where the RT term comes from here. Okay. Now, let's look at this one together, right? Let's get this one together. So what's Kp for this gas phase reaction given Kc? And that's kind of, I guess, where they use C, right, exclusively. Because when you're comparing Kp and Kc, you have to kind of make sure you know which is which. But as I keep mentioning, generally speaking, if we just see K, it's Kc, right? But here we have Kc because we want to find Kp, all right? So here, let's just look at it. So I got, you know, PCl5 gas. I got 1 mole of PCl5, 1 mole of PCl3, and 1 mole of Cl2. These are all gases, right? So over on this side, I got 2 moles. Over on this side, I got 1. So products minus reactants for a change, delta N is going to be 2 minus 1 equals 1, all right? So we're going to have like a modification, right? So Kc does not equal Kp in this case. All right. Now, let's write our units down. So Kp, Kc, R, T, delta N. All right, Kp, that's what we've got to find. Kc, 3.26 times 10 to the minus 2. If you're kind of picking this up, feel free to pause me, carry on. We'll check your answer in a minute. R, unless otherwise stated, we're going to use the standard we've always been using. Temperature has to be in Kelvin, all right, because R has Kelvin in it. All right. Temperature, what did they say? 191. 191 degrees C plus 273 equals 464 Kelvin. Finally, delta N, as we saw, 2 minus 1 equals 1. All right. So throw them in there, see what you get, right? So P equals, I'm just using the equation from up here. That one. Maybe I'll just write it just for completeness. Kc RT delta N, which equals 3.26 times 10 to the minus 2, 0.08206 liters atmosphere moles Kelvin times T, 464 Kelvin. Raise all that to the power of 1. Work it through, what you get, I get 1.2. 1.2. So in this case, literally 0.0032 is Kc, 1.2 is Kp, so they're not the same number. Okay. Remember, and you can try this math if you like, right? So if you think about it, that lot raised to the 0 would be 1, and then yeah, it's the same number, isn't it? Right. Okay. If it was no change in gas moles for products to reactants. Okay. All right. So that's how you calculate Kp. Right. So occasionally you have to calculate a number. That's how you do it. All right. Now, this next one, Q. Not that Q. This Q, right? So Q, or actually QC here, right? Okay. It's called the reaction quotient. Basically, what is Q? It's K, but not at equilibrium, right? So if you think about it, if you throw some reactants into a vessel and they start to turn into products, it takes a little while to establish that equilibrium, right? Okay, so while you're establishing that equilibrium, there's still a ratio of products to reactants, isn't there? Right? So if you like, Q is K, but not at equilibrium. It's the same expression, it's just measured not at equilibrium. If you think about it, K will equal Q at equilibrium because it's the same math, all right? But we can use Q away from equilibrium, all right? So we can work out Q before a reaction starts, right? Okay, if we start from the reactant's end or the product's end, we can work out Q and then it will go to K as the reaction progresses. Okay, now this one, you've got to be careful because it's kind of like thinking about direction. As we move forward, particularly when we talk about something called Le Chatelier in a little bit, you've got to keep kind of straight in your head, will it move left or right based on moving towards equilibrium, okay? So you put some stuff in a beaker, it'll always move towards equilibrium, won't it? Right? So eventually Q will turn into K, right, numerically, all right? But what direction is that associated with? Does it move from reactants to products or products to reactants? It's that glass half empty, glass half full thing, right? But with numbers, all right. So let's just read the key here. Given the concentrations of all reactants and products under non-equilibrium conditions, typically at the start of a reaction, right, okay, what direction will the reaction proceed in, right? In other words, will it make products or will it make reactants to get to equilibrium? Okay, are you starting from the left or starting to the right? And how do you get to the middle? Okay, so here's the thing, right? So let's think about it. What does this really mean? Now, this is what I call complementary learning, right? So there are two things, glass half empty, glass half full. If we just concentrate on one and figure that out in some detail, then we just say to ourselves, well, if they ask us the other question, it's just the reverse. We just flip our answer, right? So that's called complementary learning. So what we'll do is we'll learn one in great detail, and then if they ask us the other question, we'll just flip the answer. All right. So here we go then. This is the one we're going to learn because it's easier, right? What does it really mean in terms of reactants and product concentration when Q is bigger than K? Think about that just for a second. The value of Q, products over reactants, at that point in the reaction is bigger than the value of K, the ratio of products over reactants at equilibrium. What does that mean? Well, think about it. Because they have the same mathematical form, right? When Q is bigger than K, then the concentration of products over reactants, if you like, is too big. Yeah, it's a top-heavy fraction, isn't it? Because if it's Q, right, Q is a bigger value numerically, that means this fraction means it's a bigger number on top, doesn't it? Yeah. And eventually, if you think about it, as the reaction progresses, Q will eventually reach the value of K, that's what we call equilibrium, and then top and bottom, if you like, will have equalized, right, to their equilibrium position. All right. So in other words, when the reaction proceeds, what's going to happen? Because we've got too many products and not enough reactants, this will go down and this will go up as the reaction proceeds, right? So what must happen to reach equilibrium? So as the reaction progresses, concentration of products goes down, concentration of reactants goes up. So if you like, that's a reverse reaction, isn't it? Okay, so the amount of products goes down, the amount of reactants goes up. It's moving to the left, isn't it? So we see that down here. This is where you've got to keep it straight, right? Okay, so just read through that slowly again, or just rewind me, right? Okay, and then just get it straight in your head, right? So when Q is bigger than K, that means I've got more products than I should, because it's the same products over reactants ratio, isn't it, that defines both, okay? So if the ratio is too big, the top has to go down and the bottom has to come up to make it where it should be, K, right? So that means, hey, if I'm making products, I'm going to the left, because we understand a left to right reaction is our standard, isn't it? Okay. Complementary learning. If it's the other way round, if Q is smaller than K, right, it moves to the right. Okay. Now that makes sense. If you think about it, if I go up here, if Q is smaller than K, that means this fraction is, if you like, bottom heavy. There's more reactants than the products, right? So it moves in favor of making products. Complementary learning, right? Learn one and then just flip it for the other. Hey, when Q equals K, we're at equilibrium. That's kind of what we said, right? Okay. Now, so make sure you got in your head, if Q is bigger than K, right, that ratio is too big, so I've got to get rid of products. I get that by turning them into reactants, so it moves to the left. It's a tricky concept, but once you got it, it's easy. All right. So let's look at this. All right. So here's a worked example. We're actually going to work out the direction a reaction will go based on a comparison of K and Q, right? So let's just read it through and then do the numbers, right? So a 10-liter vessel, now remember, we're going to work out concentrations, right? So we need moles per liter. 10 liters, all right? So we're going to divide the moles by 10 in a minute. It contains this many moles of CO2 and this many moles of CO. So those are our initial conditions, right? So let's figure out those actual concentrations. It's nice and easy, isn't it, right? So it's going to be CO2 0.0015 mole. Now remember, it's in a 10-liter container. Just move the decimal place one over. 0.1, 2, 3. I'll just use regular numbers, right? In an answer, scientific notation. This guy here, and 0.1 of CO, 0.100 over 10 liters, 0.010. Okay, so those are our two initial conditions, all right, initial concentrations. So if we've got our initial conditions, now look up here real quick. It's a heterogeneous equilibrium. So when we write that, let's just do it on the side here, right? K equals products over reactants. Now that's a solid, no definable concentration. It has to be there in the container for it to work, but it doesn't include in the expression. So that's K, right? So Q is of the same form, but we're just going to put the numbers in, right? So let's do down here CO squared over CO2, which equals, so remember, the initial condition is away from equilibrium, defined by Q. Usually we choose initial conditions for Q. All right, so it's CO squared, 0.0100 squared over 0.00015. No units, I'm just gonna leave them out. And I get, for that one, 0.66. So that's the numerical value, right? Now, who's bigger, who's smaller, all right? What have we found out? K is bigger than Q, or if you like, Q is smaller than K. All right, so what does that mean? It means, since K, sorry, let's do it, right? So Q is smaller. That means this ratio at the beginning, right, is smaller than it should be, isn't it? Right? This ratio is smaller than it should be, right? That means there's more CO2 than there should be. So CO2 is going to go away and CO is going to be made. What direction do we go in? Well, we're making CO2. It's going to move to the, you tell me. Move to the right, doesn't it? Okay, so let's write that in there. Q is smaller than K, therefore, if you like, let's do this. Products over reactants is too small. Therefore, to make that bigger, okay, this is going to go away and this is going to increase. We make products, moves to right. And that's what you want most of the time. You want to throw your reactants in the vessel and make products, don't you? So that's kind of what we want. Okay. Now, try this one, right? Try this one. Similar. Again, the math's not too hard. It's that famous Born Harbor one again, right? Okay, so try this one. Michael Jordan is the answer. Okay, so when you work out the value of Q, it's 23, and then you compare it, right? Okay, all right. So actually, why don't I give you just a minute to work on that, all right, and I'll come back and solve it. Okay, you're back? All right, so let's do it. So Q equals, for this one, products, so NH3 squared, it's that Born Harbor thing, N2, H2 cubed, right? Careful, 1 mole, 3 moles, 0.5, in 50, right? So on the fly, I'm going to do this. Ready? So I've got 0.5 moles of this guy, and I'm going to divide it by 50 to get moles per liter. Square it. N2, 1 over 50. That's right. And then this guy here, 3 over 50, but cubed. Okay. And that equals 23. All right, so when you work it out, that equals 23. Now here's the question, right? So remember, Q, is it bigger or smaller? It's the one we like, isn't it, right? Q is bigger than K. That means product over reactant, if you like, is top heavy, yeah? So products have to go away and reactants have to form. It's reverse reaction. So the question says, will more or less NH3 be present? Well, NH3 is a product, right? And it moves to the left, so less is the answer. Okay, hopefully you got that one. Again, it's all about keeping it straight in your head, right? Okay, it comes with practice. All right. All right. Next one. I'll introduce the topic, then it's time for a quick break. Time flies when you're having fun, right? Now, this one, named after a famous French chemist, Le Chatelier, right? You have to say it in a French accent. There it is, right? And my little joke is it kind of reminds me of a Rambo movie, because if you push Rambo, what does he do? He pushed back, right? That's the famous Rambo quote, right? He pushed me, I push him back. He drew first blood. Okay, I'm sorry. Okay, so the bottom line is, remember, an equilibrium is an equilibrium for a reason. It wants to be at its most energetically stable. That means a certain ratio of products to reactants, okay? So if I change something, it's going to get back to that ratio. So there's some neat tricks you can play here, right? So if I have some reactants and products at equilibrium sitting in a vessel and somehow I remove some products, more reactants will turn into products to get that ratio back, okay? And this is how we actually make products in a chemistry lab or an industry, right? We actually oftentimes, if they're gas phase, for example, have a very cold surface in there, and hopefully the product will form a liquid and condense and then be out of the gas phase, right? Remember, liquids, solids don't appear in the equilibrium expression, right? So what will the reaction do? It will make more product to get back to that equilibrium position, okay? So remember, the key fact is, for A in equilibrium with B, simple example, products over reactants is a constant number. So the amount of products and the amount of reactants has to be in that ratio. The numbers can change top and bottom, but their ratio is a fixed number, right? So if you think about it, this is where Rambo comes in, right? If you change it, you're away from equilibrium all of a sudden, right? If you remove something or add something, you're away from equilibrium. So it will react that excess thing away and turn it into the other and get back to equilibrium. So if they increase the amount of reactants, it makes products. If they increase the amount of products, it makes reactants. It gets back to that K value, yeah. So it's kind of a further application of Q, isn't it, right? Okay. So you kind of, you know, in your own words, if you wish, right? So what must happen, right, if B is reduced by removing it from the reaction mixture? Like I said, maybe it's condensed out, right? Maybe it forms a liquid at a lower temperature, right? So if A is in equilibrium with B, right, and I remove some B, yeah, that ratio of A to B has to be fixed, right? So some more A turns into B, right? Reactants turn into products. So we re-establish that value for K, okay? And this is how Born-Haber, remember we talked about Born-Haber, right? This is how he tweaked it so he was getting reasonable amounts of ammonia, yeah? This is what chemical engineers do all the time. They tweak positions of equilibria by, you know, changing temperature, pressure, and things like that, which we'll see as we go. Okay, now changing pressure is essentially removing a surrounding gas, isn't it, right? So think of this as a pressure change, right? So let's think about it for a second, right? So here is the famous Born-Haber reaction, yeah? Nitrogen, hydrogen, in equilibrium with ammonia. If we think about this, right? So you push me, I push back, right? So some ammonia is removed. This is what they do in industry, right? They condense the ammonia gas, right? It has a much lower boiling point than the others, all right? So if I remove that through condensation, say, right, what does so think of this in a container, yeah? So this ratio, products to reactants, has to be fixed, doesn't it? Because that's K, right? Okay. If I remove some ammonia, I'm going to turn reactants into products to make more ammonia to bring me back to where I should be, yeah? So some ammonia is removed from the reaction vessel, its partial pressure is reduced. What will happen to the equilibrium? We like to say move to right. Make more NH3. And it's like, you know, as we lose reactants, we make products. So you can think about it as either replacing the NH3 that was lost or reacting away the reactants to get it back where it should be, okay? So either we increase the top of the fraction or we decrease the bottom. We actually did both at the same time, but you can think about it either way, all right? Try the next two, try the next two. How to think? Some N2 or H2, because they're both reactants, doesn't matter which one we choose, both, either or, all right? If we add reactants, when there's too many reactants now, right? And so that means our fraction's off. So our bottom, if you like, is too high, right? The fraction is too small. So what do? We want to get back to where we were, so we add reactants, we remove reactants. How do we remove reactants? We turn them into products. Moves to right. Okay, same effect, right? So removing ammonia has exactly the same effect on the equilibrium as adding reactants, yeah? Too little product is the same really in terms of how it works as too much reactant, isn't it? Because I want to kind of move from here to here. Ah, okay. Some N2 is added to the reaction vessel. Well, I'm asking you the same thing here, right? So I'm actually going to change that. You'd never do this in industry, right? Born-Haber's rolling in his grave somewhere, right? So some ammonia is added to the reaction vessel. What happens there? Well, if you think about it, if we add some ammonia, it's going to go back the other way because there's too much ammonia now. It's going to turn it into reactants. Move left. Okay, left. Okay. There's my slide. It says it mentions slide, right? Okay, so this is a nice slide because it shows you that even though the numbers change, we're removing and adding things, right? So they're not going to go back to the same numbers they were before we removed and added, but their ratio will be the same, if that makes sense, right? So here's one, right? So here's the, here's actually the last one without changing it, right? So here's some reactants and products in a reactor, right? So we've added these reactants, they turn into this product. These are the amounts sitting there in the reactor at equilibrium, right? What we do is, this is not how they do it in industry, but it's a way to do it, right? You could throw in some more N2, right? If you throw in some more N2, all right, that means this goes up. That means I've got more reactants than I should. What you're going to do, you're going to turn them into products, right? So really, it's just like the B example here, isn't it? Right? It's just like the B example. It's just like the B example, right? So I add some N2. This one goes up, yeah. Now, if you think about it, I didn't add any more H2, right? So that stays where it was until I add the N2. Then they react together, and they both diminish, right? Okay. And what do they turn into? NH3, which goes up, right? So I've got my new levels of these things. If you want to do a quick back of the envelope calculation, get a rough idea for that number, and that number, throw them into the K expression and you'll get a constant, right? Get a rough idea for this one, and this one, throw them in and you'll get that same constant. So it's just like your iron lab, yeah? So you had different conditions of concentration for each individual reactant and product in different trials. But they all, when you do the math, they all come to the same K value, and that's what's happening here, all right? So these ratios and these ratios, when divided out according to the math, are the same, all right? So we can predict, right? So Le Chatelier is all about prediction, okay? My time is about to go off, so I'll stop now and come right back. Okay, so as I just mentioned, Chatelier is all about predicting the direction a reaction will go based on an external stress, okay? And remember, it's going to get back to where it was, so it does the opposite, right? So you push me, I push you back, we're back where we started, right? Okay, so always have that in your mind, right? Chatelier does the opposite on the microscopic level to what we do on the macroscopic level, and that's how we as chemists or chemical engineers control equilibria, okay? We change external conditions of pressure, temperature, things like that, and the reaction, or equilibrium, I should say, will respond in the opposite direction. So we can make it do something by changing something out here, all right? So let's think about that in terms of this reaction, yeah? So here's a reaction, so we can probably draw this, right? Okay. So I've got some calcium carbonate. This is just chalk. If you actually just get a Bunsen burner and put it on some chalk, this happens, right? Okay. It turns into calcium oxide plus CO2. Yeah. Now, if you think about that, because these guys are solids, products over reactants, it's just going to be PCO2. If this is one that you'll see later, right? If it was a similar thing with solids on both sides, but the gas was a reactant, it'll be 1 over the gas pressure, right? So remember that for later, okay? But hey, it's a products, if you like, over 1, right? And if I had the other way around, it's 1 over, okay? All right, so closed container. So here's the thing. So K is just equal to the pressure of CO2, right? So the pressure of CO2, if you like, needs to stay the same over this kind of closed container of solids here, right? So let's think about what would happen to this equilibrium. Remember that equilibrium is still a reaction, right? Okay, even though these two things don't appear in here, they are necessary in terms of making the reaction go left or right. Okay, so it's got to be there, right? So let's think about, would it go left or right if we, first, increase the pressure of CO2. So if I increase the pressure of CO2, that's a valid thing to do because it's in K, right? So I can change concentrations or pressures, right? So if I increase the concentration of this, I've got too much CO2, right? So what does the reaction want to do? It wants to reduce the amount of CO2. It goes to the left. If you like, it makes CaCO3. Okay, so, you know, I increase the amount of CO2, it responds by removing that CO2, gets back to where it should be for equilibrium, right? As it do that, it turns it into calcium carbonate. Okay, next one, try this one. Try the next one. Trick question, no change. Solids don't appear in the equilibrium expression, so I can put in the world supply of chalk, it wouldn't matter. Okay, it's all about the CO2 because that's, you know, in the equilibrium math here. Okay, all right. Remember, solids, liquids don't affect anything. All right, in terms of the math. All right, now, so we can kind of expand on that a little bit. Okay, we can look in more detail at changes in pressure and temperature and how we can use those changes to really, you know, make more products when we're a chemical engineer. All right, so simple question. What exerts more pressure in a fixed volume container? 2 moles of gas or 4 moles of gas? Assume the same volume, right? Same temperature. What exerts more pressure? Well, if you think about it, it's nice and easy. It's going to be this one, right? Because there's going to be twice as many collisions per second with the wall because there's twice as much stuff. That's Avogadro's gas law from 101, if you remember that one, right? Okay. So 4 moles of gas exerts twice the pressure as 2 moles of gas in the same space, right? At the same temperature. Okay. So if you think about it, pressure is really, as we've seen many times now, proportional to concentration, isn't it? So think about pressure and concentration in the same way. If we increase the pressure of something, we're really increasing its concentration. Think how that would push equilibria left or right. Okay. So when we stress an equilibrium involving gases, this is what we can do, right? So we can increase or decrease the pressure inside a container, right, by either making the container bigger or smaller. Now, if you think about it, if we've made the pressure inside the container, say, right, smaller, sorry, let's rephrase that. If we make the container smaller, like an accordion, right, we squish what's inside, yeah, the pressure inside is going to go up. So the gas at that point is experiencing a higher pressure because it's in a smaller container, right? What's it going to do? It's going to reduce the pressure by turning into either reactants or products which have less gas particles. Right? So think of reactants in equilibrium with products, right? If I have 4 gaseous products, 2 gaseous reactants, under high conditions of pressure, it's going to turn into reactants because, hey, I'll make the pressure higher, it will turn more gas into less gas, it'll make the pressure lower inside. It responds in the Chatelier way, right? So we can kind of write that down. So when an equilibrium involving gases is stressed, by altering the pressure, the equilibrium will shift to either increase or decrease pressure by removing or making more gas molecules, right? So think about it, right? So when the pressure is increased, we squeeze the container and make it smaller. The pressure goes up. What's the mixture going to do? Remember, it's a mixture of reactants and products. It's going to make less gas, right? So it will remove the stress by removing moles of gaseous material, right? So either the reactants or products will have more moles of gas, whichever has the less, it will turn into that. All right. Complementary learning. When the pressure is decreased, we make the container bigger. Suddenly there's, you know, less pressure in there. It will make more pressure. It will increase. It will increase the number of moles of gas. Okay, so that's the take home. Chatelier is, remember, the opposite, right? So if I increase the pressure inside a container by making it smaller, the gas inside will respond. So it wants to get back where it was. It will make the pressure less by turning into the thing, reactant or product, with less gas molecules. Other way around, if I expand the container, make the pressure less inside, it will respond by making more pressure, make the reactant or product with more gas particles. All right, that's your concept. So here's one in action, right? And actually the picture is pretty accurate. If you want to count the numbers of molecules in the picture, it actually is legit, so to speak. I'm reminded of something. Too legit to quit? Yeah. All right, so here we have 1, 2, 3, 4 species, right? Or species, right? Species, I'm not sure. But they're in a ratio. 1 reacts with 3 to make 1 and 1. This is what I like to do, right? Whenever I'm looking at one of these problems, I say, hey, there's 4 moles of, stoichiometrically at least, 4 moles of gas as reactants, but only 2 moles over here, right? So if you think about it, the products will exert less pressure than the reactants, yeah, because 4 moles exerts twice the pressure as 2 moles. So if you like, we can put these gases in a container where we can change the volume, like a piston in a car, right? So here we have, here we have our reaction vessel, if you like, right? Here's our reaction vessel. And we can literally count the molecules, right? We can literally count the molecules, right? So an easy one to count would be maybe methane, right? CH4. So CH4 is this one. Yep. CH4 is this one, and there's 2 here, and we'll see what happens, right? Okay. So let's look at this. Yeah, let's look at this. What would happen to the reaction mixture if the vessel was compressed? In other words, the pressure outside, well, the pressure, let's just say generically, pressure goes up, right? So we're making the pressure inside go up by squeezing it, yeah? That's what we've done here, yeah? If we go back to our equilibrium, what's going to happen here? So if the pressure goes up, think about it, it wants to get back to the pressure it was at, right? So what's the equilibrium going to do? Make more or less gas to make the pressure go down inside. We've increased the pressure inside by squeezing it. It responds by doing the opposite, getting rid of that stress, right? Reversing it by making the pressure lower. What's less pressure? More or less molecules? Less, right? So it's going to turn 4 into 2 because 2 has less pressure than 4, right? CH4, as we mentioned, is a product, so it's going to move to the right. We're going to make products. So if I worked in industry and I wanted to make some CH4 and water from these reactants, I'd increase the pressure of the container, wouldn't I? Okay, because look over here. There's our 2 was turned into 3 in this one. Our other product was water. There's 2 there and there's 3 there. So we've made more product by squishing it, because if you count the number of molecules, right, there's going to be less in here than there is in here, right? Okay. What would happen if the reaction vessel were doubled? It's going to move, if we go that way, the pressure's less. It's going to make more pressure. It's going to go the other way. Move left. Make more reactants. Okay. Hopefully that makes sense. All right. That's kind of neat, right? Now, I'll let you think about this one. All right. Can the amount of products in the following reaction vessels be increased by increasing the pressure? So it's like we work in industry. It's easy to squish things, right? So let's pretend we work in industry. We have these various reactions we're working with. Here they are, right? Can we increase the amount of products, right? In other words, does it move to the right, right? Can we increase the amount of products by increasing the pressure, right? Okay. Pause me, have a go, come back. You're back. Remember the first trick? Look for gaseous reactants and products. 1, 1, 1, 1. There's 2 there, 2 there. So that's kind of a trick question right off the bat, isn't it? Right? It doesn't matter, okay, because number of moles of gaseous product and reactant are the same. Pressure's going to have no effect. It's just, the equilibrium's just going to be if it's at its natural state, if you like. It won't be variant on pressure, so no change. Okay. Here, that's a solid, doesn't exert a pressure. Neither does that. That one is, right? So it's a bit like our previous example with the CO2, isn't it, right? So think about it. If we increase the pressure, what's the reaction going to do? Well, it's going to remove the pressure by removing gas. It's going to go that way. So no, it decreases. Product. This will react with this to make this. Fair enough. Next one. Oh, interesting. Now this, I feel some extra credit coming on. Right, 2 of these react with 1 of those to make 2 of these. This is actually the first step in what's called the contact process, okay? So research the contact process. And here's a big clue. H2SO4. The biggest bulk produced chemical in the world is sulfuric acid, H2SO4. It's what's in batteries for cars, right? And it's used industrially for all kinds of things, like getting corn syrup out of corn, right? Believe it or not. Okay, so H2SO4 is one of the biggest bulk chemicals used in the world, the biggest actually, okay? And the first step in the contact process is roasting. Well, actually, the first step is making sulfur dioxide from burning sulfur, and then you burn it even more to make sulfur trioxide. Then you do some more things with sulfur trioxide to make H2SO4. Tell me what those things are. show me the contact process. You know, there's like literally 2 or 3 equations. Give you a point, right? Remember, Wednesday is the deadline. Now, in terms of the gas problem, right? So we've got 3 gas molecules over here and 2 over here. So if we increase the pressure, what's going to happen? It's going to make less. It's going to go to the right. So yes, that one works. More product goes to the right. Okay, fair enough. All right. Now, that was pressure. All right. Always think with Chatelier, I do something to the system, it does the opposite. And then how does that translate to the equation on the page? Remember, the equation on the page is a microscopic thing. It's what's happening in the test tube. Okay. Now, so pressure, a little bit easier maybe. Okay, the slightly more kind of challenging one perhaps is temperature. But not really. If you understand the basics of thermochemistry from 101, it's not too bad, okay? So recall thermochemistry from 101, and again, we'll do a thermochemistry chapter pretty soon, and I'll review this stuff, okay? But if you want to kind of look on the Chem, actually, if I remind myself, I'll link to the Chem 101 packet so you can take a look at it, right? Okay, but you probably don't need it for now, just some simple stuff, right? So here's the word exit, right? Exit, leave, right? So exothermic and endothermic. So exothermic reactions, which 99% of reactions are, heat comes out, right? So exothermic, heat exits system. Beaker, test tube, whatever, right? So if you like to think about that, this is where it's very, very important, right? So what we're going to do, we're going to think about heat is evolved, right? It comes out. So if you like to think about it, it's a pseudo product. The product of the reaction was, yes, some new chemicals, but also a bunch of heat. That's why you burn charcoal on your grill, right? Not to make carbon dioxide, but to make heat. So for an exothermic reaction, heat's a product, okay? And we can treat heat as a product, just like we think about, you know, gases both sides, right? We can, hey, which way would it go to make or lose heat if heat's on the right? See that in a moment. Endothermic, complementary learning, heat has to go into the system during a reaction, okay? So endothermic reactions are kind of rare for reasons we'll see in the last couple of pages, but heat enters system, right? So heat has to go in to make the reaction go, okay? So it's the reverse. Exothermic reactions, it liberates heat. Endothermic reactions, if you actually hold on to them, would feel cold because they take heat from the surroundings, i.e. your hand, right? So if you're holding a reaction in which an endothermic reaction is happening, it feels cold because it's taking heat from your hand to work, okay? If you're holding something that's on fire, it's an exothermic reaction that feels hot because heat's coming out, okay? So again, most reactions are exothermic. Think about burning, right? That's an exothermic reaction every time. Okay, so let's fill in a little bit of a table here, okay, just to catch up on some details, yeah. So exothermic reaction, observation, heat evolved. If you're holding the container, you get a hot hand. I'll put it in speech marks like that, right? Right heat where? Well, in a pseudo-balanced equation, where right heat is a product because it comes out of the reaction, right? So we'll see that in a second. Now remember, that's basically plus Q, isn't it, right? Remember the first law of thermodynamics? Delta H equals Q, but hey, it's a directional thing. So energy lost by the chemical reaction equals the energy that comes out as heat. That's really this here, isn't it? So minus delta H, sign of enthalpy, is a plus Q. So remember, if it's exothermic, heat comes out minus delta H. What's lost by the reactants and products, right, in the reaction, sorry, what's lost from going from reactants to products in terms of energy comes out as heat. It's an exchange, thermodynamics, heat exchange, right? Endothermic, opposite. Heat absorbed. Remember, if you're holding a vessel in which an endothermic reaction is happening, it feels cold because it's taking heat from the surroundings, your hand, cold hand, hand, cold hand. All right. So heat is on the other side, right? So it's the opposite. So it's a reactant. So when we do these Chatelier things with exothermic reactions, we'll write heat as a product and then think, hey, adding or subtracting heat, what happens? Endothermic, we write it as a reactant, adding or subtracting heat, what happens, okay? And the sign of endothermic is reverse from exothermic, right? Positive. Okay, so the amount of heat evolved, exothermic or absorbed, endothermic, is expressed in the form of a balanced thermochemical equation. You've seen these before from 101. So for a process, right, you'll see that, yeah. So you'll have delta H equals minus 206, for example. It's a combustion. So minus means it's what? Exo or endo? Exo, right? Okay, so that's an exothermic reaction, right? So we're going to write heat as a product. So for this one, and I'll just get to it in my notes real quick. Actually, I don't have that in my notes, so I'm going to write it right now. We're going to say CO gas plus 3H2 gas in equilibrium with CH4 gas plus H2O gas. And because this is a big clue, right? It's an exothermic reaction, I'm going to write heat as a pseudo product, okay? Once we've written it as a product, think of it now like adding or removing reactants to establish equilibrium, right? Okay, so now let's think about this. What happens to the position of the equilibrium? That's code for, does it move to the left or to the right? Does it make reactants or products when you stress it? Okay, so when we heat this thing up, think about it. So we're going to put a fire to this thing, right? So we're going to add heat, right? So it's in a container, we're going to heat it up. Chatelier's principle, what's Chatelier going to do? Remove heat. How does it remove heat? Well, heat's a product over here, isn't it? It's on the right. So we're going to remove it by moving to the left. So if the reaction is exothermic, heat comes out this way, it's endothermic that way. It's going to react endothermically to remove heat. Moves to left. Makes reactants. You get that? Yeah, so for an exothermic reaction, if you heat it up, it moves in favor of reactants. That has some consequences we'll see later. If you cool it down, right, if you cool it down, what's going to happen? Well, you're in the container, you're at the equilibrium, right? Now you're being cooled down. You want to get back to where you were, so you heat up. What do? You make heat. Heat's a product. You move to the right. Moves to right. Makes product. And heat, if you like. Does that make sense? So when you cool the vessel down, it responds by doing the opposite to get back to where it was, right? So it makes heat. How does it make heat? It turns reactants into products because that makes heat exothermically. All right. Now we have this reaction, which is, boom, careful, endothermic. So I'm going to write heat as a reactant because it's endothermic, right? So, question, chemical engineers, is a high or a low temperature favorable for the formation of CO, which is a product, right? Want to make some product, want to make some CO. Do I heat this thing up? Yes or no? Think about the consequences, right? If I heat this thing up, what's it going to do? It's going to want to remove heat. Heat's on the left there, so it's going to go that way, right? There you go. So if I heat this thing up, it's going to want to remove heat. It's going to go to the right. Think about it, glass half empty, glass half full. If I remove heat, what's it going to do? It's going to make heat. It's going to go to the left, okay? So what we want to do, we want to heat it up. And that's the great irony of science, right? So you have these very low amounts of, well, I'll talk about it in a minute, right? So endothermic reactions, heat them up, you get more product. Exothermic reactions, heat them up based on equilibria, you get less product. Interesting. That's our last two examples, right? Okay, so now you've seen the effect of thermochemistry, right? And moles of gas, yeah? Pressure and temperature. So you've seen the effects of pressure and temperature. So now you can fiddle with those variables to optimize the amount of product you formed, right? And if you go back to that Haber process, you can actually look it up online and you can kind of see the conditions compared to room temperature and pressure, and you can predict how it works, right? So if you look here, so here's the Haber process, yeah? Okay, it's exothermic. I'm writing heat as a product. Okay, so let's do the heat first, yeah? So what conditions of temperature and pressure would be most favorable for the formation of product ammonia, yeah? Well, let's think about it. If I cool this down, is it going to go left or right? If I cool it down, it's going to want to make heat, yeah? So it moves to the right if I cool, yeah? So, decrease, all right? So we see a decrease in temperature will make more product at equilibrium because it's an exothermic reaction. Remember the concept, right? If I cool it down, it does the reverse. It makes heat. It's an exothermic reaction. It moves to the right. Okay. Now, this next one, interesting. I got 4 moles of gas as reactants, 2 moles as products. I want to make more ammonia, so I want to make less gas, right? So what external force would cause the equilibrium to make less gas? Well, less gas exerts less pressure, doesn't it? Right? So if you think about it, if I increase the pressure, it responds by lowering the pressure. How does it lower the pressure? Makes less gas, right? So increase the pressure. Okay, so if I increase the pressure, I think, you can look at the number, I think it's like 10 atmospheres or something in an industrial reactor, and a pretty low temperature. Now remember, the rate of a reaction is proportional to its temperature, right? The faster the molecules move, which has consequences, yeah? So it eventually gets there. You have to kind of heat it gently, and it eventually gets to the point where you make lots of ammonia, all right? And we'll talk about that in a second some more. All right, so try these, or try this one, What conditions of pressure and temperature, so just like the one before, what conditions of temperature and pressure would make more CO products, right? Okay. Now it's endothermic, so heats a reactant if you like. All right, okay. Give you a second, come back. All right, so if I want to make it go that way, right? Heat's a reactant, right? So I want to remove heat, so I do what? Actually, that's just, I'm going to fall into my own trap. Right? So what conditions of temperature and pressure would maximize the formation of CO2? If I add heat, right, it's going to want to remove heat. So it's going to go from left to right. So add heat, so increase heat. Okay, saw that before. Okay. What about gases? Well, there's 2 over here and 3 over here, right? So if I want to make more products, yeah, that's more gas molecules, which exert more pressure, right? So what I'm going to do the reverse, right? So if I lower the pressure, it's going to make more gas to increase the pressure. So lower P. So if this reaction was mine, I'd heat the thing up in a big container, so it's a low pressure and a high temperature. Boom, I'd make more product. Okay. Now, back to my previous comments, right? So as you may have seen, I've been alluding to it all along here. This is kind of a cosmic joke, right? Okay. So what happens to the rate of any exothermic reaction when it's optimized? So an exothermic reaction, as we just saw with ammonia, all right? Most good reactions are exothermic, right? So heat's a product, right? So if I want that to work and get more product from an exothermic reaction, happens at a lower temperature. But what did you just learn last week or the week before about kinetics? The lower the temperature, the slower the reaction goes. Okay, so essentially it's a catch-22, yeah? So for 99% of reactions are exothermic, right? Increasing heat lowers product yield, which is B, right? Okay. But you need to increase the heat because you need the rate of reaction to be high to get there anyway. So you're making less stuff fast. That's the catch-22, and it's kind of the cosmic joke, right? So the cosmic joke is kinetics versus equilibrium, right? 99% of reactions are exothermic, right? Okay. So if I add heat to them, I'll make less product because the equilibrium will shift to the left. All right. But I have to have a certain amount of heat to make the reaction go quicker. So I wait forever to make more stuff, or I get little stuff really quickly. That's the cosmic joke. Okay, I hope you got that one. Okay, so that's kind of interesting. Okay, you just can't win. So as I say down here, you can make less stuff fast, right, high temperature, or more stuff slow, low temperature. You can't win either way. Okay. All right, that was our previous question. There was one more thing. Okay, now this one, I'm actually going to set it as a, I'm feeling super generous. 1, 2, 3, 4, 5. Out of 5 points, right? So again, you know, it's casual, right? It's not like a real test or anything. So you can, you know, take a picture of this with your phone, all right? Make sure I can read it. Write equilibrium expressions for these 3, okay? And then work out partial pressure of SO3 algebraically, okay? So you have a KP here, you do algebra to find a pressure, and then just equilibrium expressions. And I'll take a look at that, okay? All right, and get that to me by Wednesday. Okay. All right. Stop there. See you guys next time.